The Haber-Bosch process, from industrial backbone to geopolitical fault line and catalyst for green transformation. The synthesis of ammonia via the Haber-Bosch process represents one of the most consequential achievements in industrial chemistry, underpinning modern agriculture and global food security. Since its development in the early 20th century by Fritz Haber and its subsequent industrialization by Carl Bosch, ammonia production has enabled the large-scale fixation of atmospheric nitrogen, supporting a substantial fraction of the global population through fertilizer use. It is estimated that synthetic ammonia-derived fertilizers sustain nearly one-third of humanity, highlighting the central role of this process in societal development. The Haber-Bosch process involves the catalytic reaction of nitrogen and hydrogen gases to form ammonia according to the exothermic equilibrium reaction. N2 plus 3H2 equals 2NH3 delta H equals minus 92.4 kilojoules per mole. From a thermodynamic standpoint, low temperatures and high pressures favor ammonia formation. However, the intrinsic kinetic inertness of molecular nitrogen, arising from the strong N triple bond, necessitates elevated temperatures to achieve practical reaction rates. Consequently, industrial operation typically occurs at temperatures of 400 to 500 degrees Celsius and pressures of 10 to 30 megapascals. These conditions represent a compromise between equilibrium conversion and reaction kinetics, with continuous recycling of unreacted gases employed to enhance overall yield. The catalytic system is central to the efficiency of the Haber-Bosch process. Conventional industrial catalysts are based on iron derived from magnetite or wüstite precursors, promoted with additives such as potassium, calcium, and aluminum oxides to enhance activity, stability, and resistance to poisoning. The mechanistic pathway involves dissociative chemosorption of nitrogen on the catalyst surface, followed by stepwise hydrogenation of adsorbed nitrogen species to form ammonia. Among the elementary steps, the cleavage of the nitrogen-nitrogen triple bond is widely accepted as the rate-limiting step, as demonstrated by extensive surface science investigations, notably those of Gerhard Ertl, whose work elucidated the adsorption and reaction dynamics on iron surfaces. Despite a century of optimization, the Haber-Bosch process remains highly energy-intensive. Modern plants are typically integrated with hydrogen production units based on steam methane reforming, SMR, where natural gas serves both as feedstock and fuel. This integration results in significant carbon dioxide emissions, with ammonia production contributing approximately 1 to 2% of global anthropogenic CO2 emissions. The majority of these emissions originate from hydrogen generation rather than the synthesis loop itself, underscoring the importance of decarbonizing upstream processes. While the chemistry of ammonia synthesis is well established, its industrial implementation is highly energy-intensive and deeply intertwined with fossil fuel infrastructure. Hydrogen is conventionally produced via steam methane reforming, making ammonia production a significant contributor to global carbon dioxide emissions. Modern ammonia plants are optimized for large-scale, continuous operation, relying on centralized production and global distribution networks. This model has historically delivered high efficiency and low cost, but it also introduces systemic vulnerabilities, particularly in times of geopolitical instability. The recent conflict involving Iran and the disruption of maritime transport through the Strait of Hormuz has exposed these vulnerabilities with unprecedented clarity. As a critical choke point for global energy and chemical trade, the Strait of Hormuz facilitates the transport of natural gas, ammonia, and nitrogen-based fertilizers from major production hubs in the Persian Gulf. The effective blockade of this route has led to a decoupling between production capacity and market accessibility, stranding significant volumes of ammonia and fertilizer while triggering global price volatility. This disruption highlights a fundamental limitation of the current Haber-Bosch paradigm. Although ammonia synthesis can occur anywhere with access to nitrogen and hydrogen, its economic viability has historically depended on centralized production in regions with cheap fossil resources and established export infrastructure. When these supply chains are interrupted, the consequences propagate rapidly through agricultural systems. Fertilizer shortages and price spikes directly impact crop yields, particularly in import-dependent regions, thereby amplifying risks to global food security. From a process engineering perspective, the crisis underscores the dual dependence of the Haber-Bosch system on both feedstock availability and logistics. The blockade not only restricts the transport of finished fertilizers but also affects upstream inputs such as natural gas, increasing the cost of hydrogen production worldwide. This dual disruption reveals the inherent fragility of a system optimized primarily for economic efficiency rather than resilience. In this context, the transition towards sustainable and decentralized ammonia production becomes both a technological and strategic imperative. Electrified Haber-Bosch systems, powered by renewable energy and coupled with hydrogen generation via water electrolysis, offer a pathway to decouple ammonia synthesis from fossil fuels and geopolitically sensitive supply chains. Such systems can be deployed at smaller scales and closer to points of consumption, reducing reliance on long-distance transport and enhancing regional self-sufficiency. Recent advances have focused on transitioning toward green ammonia, in which hydrogen is produced via water electrolysis powered by renewable energy sources such as wind or solar. This approach decouples ammonia synthesis from fossil fuels and can substantially reduce life cycle emissions. For example, replacing SMR-derived hydrogen with electrolytic hydrogen can reduce CO2 emissions per ton of ammonia by more than 70%, depending on the carbon intensity of the supply. Moreover, the electrification of compressors and auxiliary systems further enhances overall energy efficiency by eliminating losses associated with steam-driven machinery. In parallel, significant research efforts are directed toward developing next-generation catalysts capable of operating under milder conditions. Ruthenium-based catalysts, as well as emerging materials such as nitrides, hydrides, and electrides, have demonstrated superior intrinsic activity compared to conventional ion systems, particularly at lower temperatures and pressures. However, their widespread adoption is constrained by cost, sensitivity to impurities, and challenges associated with equilibrium limitations at reduced pressures. The interplay between catalytic activity and process design remains critical, as lower pressure operation often necessitates alternative ammonia separation strategies. Traditional ammonia separation relies on condensation at high pressure, which inherently favors operation at elevated pressures. Innovative approaches, such as absorption-based separation using metal halides or other solid sorbents, have been proposed to enable efficient ammonia removal at lower partial pressures. These developments could facilitate the design of modular, small-scale Haber-Bosch systems suitable for distributed production, particularly in regions with abundant but intermittent renewable energy resources. The integration of renewable energy with ammonia synthesis also introduces new operational paradigms. Unlike conventional large-scale plants optimized for steady-state operation, future systems must accommodate fluctuating energy inputs. This requirement necessitates catalysts and processes capable of rapid startup, shutdown, and load variation without significant performance degradation. Advances in electrolyzer technology, particularly proton exchange membrane and solid oxide systems, are expected to play a pivotal role in enabling such flexible operation. However, further improvements in efficiency, durability, and cost are required. Beyond its traditional role as a fertilizer precursor, ammonia is increasingly recognized as a potential energy carrier and storage medium. With a high hydrogen content, 17.6 weight%, and established infrastructure for storage and transport, ammonia offers a carbon-free alternative for energy applications, including fuel cells and combustion systems. Its use as a long-term energy storage vector could complement short-duration storage technologies such as batteries, thereby facilitating the integration of renewable energy into global energy systems. In conclusion, the convergence of chemical engineering, energy systems, and geopolitics has redefined the role of the Haber-Bosch process in the 21st century. While its foundational chemistry remains unchanged, its industrial implementation is increasingly challenged by environmental constraints and global instability, as exemplified by the disruption of supply chains through the Strait of Hormuz. The recent crisis demonstrates that a process optimized for centralized, fossil fuel-based production is inherently vulnerable to external shocks. Moving forward, the resilience of global fertilizer and energy systems will depend on the evolution of the Haber-Bosch process toward decentralized, electrified, and low-carbon configurations. By integrating advances in catalysis, renewable energy, and process design, ammonia synthesis can transition from a source of emissions and geopolitical risk to a cornerstone of sustainable development. In this reimagined framework, the Haber-Bosch process will not only continue to sustain global agriculture but also play a pivotal role in enabling a more secure, distributed, and carbon-neutral energy future.